Welcome to EDU World Space.
Okay, so for part A here, let's go ahead and use S10 to approximate or estimate the infinite sum S. And also, we'll also ask how good is the estimate?
Here's a clean and professionally formatted presentation of the calculation shown in the image. Application of the work energy
Here,
theorem,
by
WET.
S10,
From the
of
work
course,
energy
we
theorem,
mean
the
the
force
nth,
F
the
is
10th
given
partial
by
sum.
F equals frac
So
text
solution
KE,
for part
where
A,
KE
so first
equals
we'll write
kinetic
out
energy,
S10
S will stop
by
distance.
definition.
I'm given for object A,
This is the
FA
sum
equals frac
of S
100,000,
just for the
0.10.
sum from
For
1
object
to
B, FB equals
10.
frac 225, 1500 equals 0.15
So in
times
that
base
case,
n. And force ratio frac
just go ahead and
FA,
write out the few
FB
terms here
equal frac 0.10, 0.15
and add
equal
up a bunch
frac
of
2 mole result.
fractions.
About
This will
frac
take quite a
FA,
while
FB.
here, so
Would you like a
one
PDF
could go to the
version of this
calculator
explanation?
and just round off here. Let's see, 1.549768. And then, so that's an approximation to S. Now to answer the second question, how good is the approximation? Well, if you look at exercise 34, you'll see that they give the value for S for this sum here, the infinite sum, given by Euler. So in our case, the error is the difference between the exact value and the approximation. So since we now have the exact value, we'll plug that in, and we'll also plug in our approximation, S10. And in this case, we're getting about 0.0952, which is less than 1 over 10. So it's not a bad approximation because it's less than 1 over 10, but we can do better by taking larger n. So it's not a bad estimation considering we only use 10 terms, but 1 over 10 just might not be accurate enough depending on what its purpose is. So let's go on to part B. Now for part B, this is where we'll actually go ahead and improve the estimate from part A using inequalities 3 and plugging in n equals 10 into 3. So let's go ahead and solve this. So solution. So first, let's recall from part A what we found. We found that S10 was about okay, so now we look at inequality 3. It gives upper and lower bounds for the exact value in terms of Sn and these integrals here. So notice the difference in the lower bounds of the integrals. One's at n plus 1, the other one's n. So here, because we're to use n equals 10, so that determines that. And if you recall from our series, an is 1 over n squared, and so that means f of x should just be 1 over x squared. So let's go ahead and plug all this in here. Okay, so then now we could actually just go ahead and integrate this. We do have improper integrals here, but these ones are not too bad because when you plug infinity, the expression becomes 0. And so that would become S10 plus 1 over 11 less than or equal to S less than or equal to S10 plus 1 over 10. So that now one would use the information from part A and plug that in for the S10s here. So plug those in for S10 and then add the fraction. And so going on to the next page, I'll write this out. So there's S10 plus 1 over 11 and then S10 plus 1 over 10. And then just add those together. And there we go. Now to find a value for S here, so think of it this way. We have an interval here, a lower and upper bound. And all we know is that S falls somewhere in between here. So instead of choosing either of the endpoints, another approximation would just take the midpoint of these two, the average. And so here, we'll take S to just be the average here. So as an approximation to S, and this becomes also, we'd like to know the error involved here. And so there's a few ways to do this. So this is our approximation for S. And so since it's in the middle, the error is just half the length of the interval. And similarly, you can do this half if you like, but because we chose the midpoint, these two halves have the same length. So that's one way to write it, or you can just take the entire interval length and divide it by 2. So the entire interval length, it would be the rightmost endpoint minus the leftmost endpoint and divided by 2. So this would, this is the length of the interval here. And if you go to the calculator, you see that this is indeed less than the 0.005. So the error is improved by using, in part B, by using the midpoint S. Now let's go on to the next page for part C. This is where we'll compare the estimate in part B with the exact value that we mentioned in part A, but this is coming from number 34. So this is in exercise number 34. So solution. So from part B, we had an approximation, an improved estimate for S. So let me write that down, 5222. And we also saw what the error bound was. So if you look at number 34, as we mentioned, this gives the exact value due to Euler. So in this case, we see that the error given by using this value S go to the calculator here, 0.0288, and that's also less than the 0.005. So this shows that the answer we're getting from part B is very, very close to the exact answer here. Okay, so we have one more part here, part D. This will be the final part. This is where we'll find a value of n. You just need one value. That'll ensure that the error in the approximation is less than 0.001. Okay, so solution. Well, we don't want to use n equals 10 anymore because that's not a good enough approximation. So instead, we won't plug in a value for n yet, but we'll use this inequality for the error here. So this is for the remainder when using n terms. So this will be 1 over x squared. That's our f of x. All right, so it's pointing at that to remind us where the 1 over x squared is coming from, and we want this to be less than 0.01. This is what we want. And so we're going to solve n to make sure we get what we want. So let's just go ahead and evaluate that integral there. That'll be a negative 1 over x from the power rule. And then if you plug in infinity, you get 0. If you plug in n, you get 1 over n. Simplify this, and then we get n is bigger than 1 over 0.001, which is 1,000. So any value of n larger than 1,000 would work. So the smallest one that you could possibly use is 1,001. Any larger n would work, but here all they ask for is a value. So in that case, we can just use this value here. And by what we just showed, taking this value of n will ensure that the exact answer minus this value here, the 1,000 in first partial sum, will indeed be less than 0.001. And so that resolves the problem.